Hey everyone, and welcome to the next session on this mini series on machine learning by Quant Masters. So, this is Shashank, your technical trainer, where we're going to take a look at what exactly makes statistics superbly important in order to perform machine learning. We often look at a lot of machine learning tutorials, we often look at a lot of books on it, and we often see that statistics seems to be the underlying concept. Statistics seems to be the base on which, or the foundation on which, entire concept of machine learning is built. That is no further than the truth. Today we're going to take a look at why exactly statistics is considered to be the basic thing without which we literally cannot perform machine learning. So for us to understand this, we first need to know that in order to be a good data scientist, in order to be a really good machine learning engineer, in other words, there are three things which we need to know very, very well. One of them is a good programming language, which we get to choose. That could be either, as we learned in our last session, could be Lisp, could be Python, could be R, could be Java, could be C++. You literally can choose anything. We prefer to choose Python for obvious reasons that we saw in our last episode of this mini series. Apart from programming languages, the next thing to consider is domain. Think about this. We really cannot perform machine learning in a certain domain unless we know the knowledge in the domain. For instance, if I want to predict the next COVID wave when it may happen, for instance, I need knowledge of data. I need to know and understand what each of this data means in order to predict further. Unless I know what this means, I cannot predict further whatsoever. That's one scenario. Now, the second scenario here is, take one more example. If I want to predict stock prices, unless I know about the domain of stock prices, I can never predict it. So, this is where domain knowledge is important. Now, apart from this, there's one more hugely important part that's called statistics, which is most often overlooked. And people think that, hey, it's machine learning. I just need coding in order to be a good machine learning expert. I don't need statistics at all. This is what we generally think of. And this is where most of us go wrong in the foundation of machine learning itself. Because without statistics, we literally cannot perform machine learning whatsoever. So let's get to see here what kind of statistics is important. Why is it important in this session? So the first of the two kinds of statistics we often need to know is called descriptive statistics. Descriptive statistics is often used to describe some data, as the name suggests. Think of this. You have some particular data, like for example, there's some data like COVID cases. I'm just taking some example. So at some point of time, it could be less, it could be more, it could be less, it could be more, it could go like this. At certain time, because of some unfound situation, like for example, 3 days no testing will be done. Suddenly, 1 day testing will be done. It may go high and come back, and then it may go like this. Now, this is not a normal scenario compared to others. All other graphs, all other distributions are like this, whereas this distribution is very sharp and sudden. So this is what we call as an outlier scenario compared to everything else. Take one more example. If you want to predict stock prices, I'll just remove this. If you want to predict stock prices, let's say suddenly stock prices go up, come down. There's some pattern for a particular company. It may keep going like this. There's some pattern. Suddenly something happens about the company. They suddenly release a new product or something. It may suddenly rise and follow the same process. So this is what we call as an outlier. To understand these outliers and to make sure our machine learning model can know that these things are outliers and can improve its accuracy and do better, we often need to perform a lot of descriptive statistics. Another reason why descriptive statistics is performed is to understand data. Think of this. Initially, you have certain data. For instance, you want to figure out air pollution, like air quality index is what you want to figure out. and you have certain input like number of vehicles that a city is driving and everything. And generally, it increases during weekdays and decreases somewhere during weekends. It increases during weekdays, decreases during weekends, and so on. So this is the pattern you can find out. So all these patterns we are able to realize by using statistical methods. So it may be a histogram, it may be a graph, it may be a probability distribution function, it may be a distribution chart, whatever it is. All these are known and identified by using simple statistical methods. That's why descriptive statistics is hugely important in order to understand how the data is currently represented. So we can understand it better and we can see where outliers exist. This is one scenario. Another scenario is if you want to perform something called inferential statistics. Inferential statistics is where you want to perform prediction. If you want to perform prediction also, statistics is hugely important. Now, I will not explain much about inferential statistics right away. I will be going through a couple of different examples up next so you can have a better idea regarding this. But before we go for inferential statistics, let's take this scenario. Assume this. There's a lot of different kind of distributions that may happen. A lot of different kind of distribution of data can happen in real life. I'll give you a simple scenario. Let's say earning. A person, if they live from the age of 0 to 80, their earning peaks from, let's say, the age of 20 to, let's say, the age of 60. So its distribution may go something like this, may just go something like this. Or let's say on the other hand, there are some cases where you're suddenly performing some operation. Most of people earn like that. Some people may earn initially and they stop earning later on, so they may retire early. So a lot of these scenario may happen, but the general scenario is that the distribution is like this. So these distributions help us understand the data, and it helps us understand if there is some extra phase which comes like this or some extra phase which comes like this. It helps us understand that these are outlier cases. These are not normal cases. So our machine learning model should focus more on these cases is what it will help us understand. So there are a lot of such examples, a lot of such scenarios that help us understand this. So this is called distribution of data. Another example that I would often take is again COVID data, or another example that you could often take is, let's say, any other data. You have a certain distribution of it. This distribution with its outliers are identified. That's where all these statistical methods are hugely useful. Now, let's take a look away from descriptive statistics all the way over to inferential statistics. This is where you start thinking about prediction. Now, let me give you one simple example. Think of this. The best example I can possibly give you is, let me go directly to NASA climate data. I think this should be one of the best examples I can possibly give you to understand some simple prediction models. So I have some examples directly available with me in our desktop itself. But rather than that, I would also want to take some real life, real world examples. So this is the website I wanted to go. I unfortunately went through a wrong website. So let's take a look at this. Let's say this is the carbon dioxide levels in the air over the last few years. Right, now don't be alarmed if you're just joining this session. This session is not about climate science, it's about data science. So I'm just showing you one example because this is one of the best examples we can use to normally understand how this works. So it still says loading vital signs, so hopefully it gets to load it. I'm trying to see if we can find any other graph here. If not, let me just explain it in a different way right away so we can wait for it to be loaded. So let me just scroll back up. It should load quickly here. All right, here it is. So I'm just unable to, yeah, here it is. You can see this. So here you can see that this is a straight line. You can easily observe this. So how can you measure this? How can you measure what will be the carbon dioxide emission in the next week, in the next month, in the next year? If you take a look at this line, it's very easy to measure. It's almost a straight line. Since it's almost a straight line, what you can do is just take the line here. Let's look at what is the x-axis and what is the y-axis so I can explain and understand this better. So if you take a look at this, the x-axis is here and the y-axis is, let's say, CO2 per millimeter. So it's going somewhere like this. Since it's going somewhere like this, all I need to do is just draw a line along it and find out what is that line equation, which is y equals mx plus c. This is our simple line equation. With this line equation, x is your x-axis data, which is the year, which could be 2020 or 2021 or 2022 and so on. And y-axis will be your CO2 parts per million, which will be something like, let's say, 350 or 400 or 450 or so on. So based on this x and y value, you can simply and easily use what we have learned in our school days. That is the equation y equals mx plus c. To take the x value as year, if I take the x value as 2022, for instance, and I calculate the y value with this equation, with the slope and the constant, I will be able to get an approximately right amount of carbon emissions for that year. Sounds like a very simple task, right? Sounds like a very simple task. So this is a linear scenario. Even if you take, let's say, global temperature rise or anything like this, you can easily look at it and figure out how to calculate it. So I'm just giving you this one example. Carbon dioxide was very easy to calculate because it was linear. We could directly take a linear equation like this and calculate it. But everything in real world is not linear. Think of COVID cases. It goes in a different way. Think of stock market share prices. It also goes in a different way. Not everything is linear. Share prices can go haphazardly. You cannot use a line equation to predict. That will go very wrong. What if it goes like this? It goes directly down. Then if you use a line equation, you're predicting very wrongly. Here, you need a different kind of model. You need different kind of equation which can move around like this. So if you remember something where we learned quadratic equations like ax square plus bx plus c, we can mark a quadratic equation in a graph, right? If you remember, we have done this in our school days. Whenever we mark quadratic equation in a graph, it comes like a parabola. I hope you guys remember this. So it comes something like this. So if you remember this, you guys can just let me know with a text. If you remember this nostalgia and if you hate maths or something, whatever it could be, you guys can let me know by text if you remember this or if you don't remember this as well. So these are the kind of equations which we generally write. So for carbon dioxide, we can easily create a linear equation. However, if you take global temperatures on the other hand, you cannot take a linear equation on this. You cannot use a line that is with the formula of y equals mx plus c to calculate something like this. If you observe this, this equation is entirely different. Of course, lately it looks like a line, but it has not always been like that. So you cannot easily calculate something like that goes like this in a straight line. Here you can figure out, but here you may not be able to accurately represent it. So for these cases, for stock market data and so on, it's going to be very, very difficult to analyze and create the right kind of prediction. So if we really want to do that, take one more scenario, take this. If you think about Arctic ice, calculating Arctic ice is a very difficult task. It's not easy. If you see here, no straight line can ever solve it. So you need different lines. So a straight line equation goes like this. Let's say a quadratic equation line goes like this. A cubic equation line goes like this. An equation line which is, let's say, with to the power of 4 may go like this, so like this. So depending on different power to it, different powers associated to the x values, you can literally calculate and try to create different kind of equations which can figure out the future values. So all of these are based on statistics. I'm just giving a very simple example. There are much more complicated examples with it, things like probability and so on. There are a lot of complicated examples we can choose from, but this is again one more simple example which can help us understand that statistics are hugely important to figure out which kind of model we are supposed to use, which kind of machine learning algorithm we are supposed to use, and what sort of statistical method are we supposed to use in that machine learning algorithm. So all these are supposed to be used by us to predict the next values, predict the future values perfectly. If we are able to do that, then we are definitely able to calculate this. Some of these seem very, very linear. They may be easy. Some of them may not be. So these are some linear examples. But if you search something on the other hand, let's say something like, I'll just give you one simple scenario. Let's say share price of some particular company. Let's take IBM for instance. I'm not even sure if IBM is listed. Okay, it is. So you can see here, I'll take some 5 years data. You can see it's definitely not a linear equation. If you draw a straight line, you will not make profit. If you draw a straight line, you will definitely not make a good profit out of this. So if you want to make good machine learning models, you need to know not just that, you need to know that there are not just linear models, there are all of these non-linear models which are hugely important. So that's where I come up to this. Your linear regression can easily create a simple line. The way it creates a line is like this. If there are 3 points of data, take a scenario. If there are 3 points of data like this, the way linear regression is done, regression is a model which can predict the future value. So by looking at this, we can say future value may come here, of course. But the simplest method to calculate is to draw a line. The line is drawn in such a way that the distance from each point perpendicular to the line must be the least. This is a literal machine learning algorithm in its working. This machine learning algorithm is called linear regression algorithm. This algorithm takes, let's say this is point 1, point 2, point 3. I'll call this as y1, y2 and y3. I'll say this is x-axis and y-axis. So with this y1, y2 and y3 values, what it does is it calculates a line where the distance from the line to the perpendicular point, I'll call this as y1 hat, y2 hat and y3 hat must be as least as possible. So if the distance is as least as possible, your line is good. Take one more scenario. If I draw a line like this, look at the distance now. The distance is larger, right? The larger the distance, the worse the model is. The smaller the distance to every point, the better the model is. So that's how you can create something like this, where you're calculating the distance, that is y1 minus y1 cap, this distance, and y2 minus y2 cap, and this particular distance, again y3 minus y3 cap. So whatever distance you get, these should be minimum. So we're gonna add all of these distances and we're gonna sum them, we're gonna create the sum of them and check whether the distance is smallest or not. So when you just add sum, there could be a scenario like you may get 1.86 and 1.87. It may not make much of a difference. So what we do here is we square all the distance to get larger values so that they show better distances. If there's a distance from 2.5 to 2.6, it's easier to understand. If there's a distance from 0.25 to 0.26, you may think it's not much at all. So whenever you square the distance, these are not exact squares. Like think of this, 6 to 7, the distance may not be so much. If one line gives 6, one line gives 7, it may not look so much. But when one line gives 36 as the distance and another line gives 49 as the distance, you can see the distance is very huge. And you can find out that there could be something in between which is much better. So what we generally do is we calculate the square of the distance from the actual points to the line that we created. And this square of the distance should be as less as possible. This is what we call as ordinary least squares method. It is one of the first statistical method we learn to create any machine learning model. So I'm just giving you a simple example. If you take a look at this scenario, you see this purple line. This purple line is created in such a way that distance from each point is calculated. Distance from every single point is calculated, and the square of the sum of the distance, if this is y1, this is y2, this is y3, the total something like y1000. So the distance from each point yi to yi cap is the perpendicular distance to the line that we created. The sum of the squares of it should be as less as possible. That is the best line which can predict future values perfectly somewhere close to these lines. That's how we figure this out. So this is the error we can identify. The larger the distance, the larger the error. The smaller the distance, the smaller the error. That's how your machine learning model finds out different lines and sees which has which has the least error. This is basically how your models work. So I'm just giving you a very small and simple example to how one simple machine learning algorithm works. Now it's not just linear. Every model will not give you a linear solution. Just like we saw, some may be polynomial. Some scenarios may be like stock market or Arctic ice sheet like we saw. They're not linear. They go in a different way. So when they go in a different way, a linear regression expression is not enough. You need quadratic. You need some polynomial regression with some x to the power of n, whatever that n could be. Could be 20, could be 30, anything. That helps you solve this better. So all these performances, all these operations you do is based on statistics. Let me give you one more scenario. Probability. When a die is rolled, what is the probability that you get 1? It is 1 out of 6. You calculate that with a probability, right? So this probability technique itself is used to predict an output. Think of this. You want to predict whether a sentence is positive or a sentence is negative. So to predict whether a sentence is positive or negative, you need to find a probability of it. Because you cannot guaranteedly say that a sentence could be positive or negative. It could be 75% positive according to your machine learning model and 25% negative. Because your machine learning model thinks that it's mostly positive, could be somewhat negative. So whatever is higher, you take that. So all of these are also measurements in terms of statistics. So in short, what I'm trying to point out here is statistics is a hugely important part for any machine learning model that you create. Whether you're going for regression, whether you're going for classification, it doesn't matter. Regression is where you're predicting a value, like stock market. Classification is where you're classifying something like to cats or dogs or something like that. So images, even there you need to classify with a certain percent of probability, with a certain precision. Everywhere we need statistics. So a lot of us may not realize this, but statistics are hugely important for machine learning. Whatever you just saw here, to use one simple line to predict, like as we saw with our carbon emissions, one simple example, like carbon emissions for let's say last 5 years is something like this. I'm just taking some example. Last 5 years is something like this. If last 5 years carbon emission is something like this line will be of no use because the distance from each point, square of the distance from each point, let's say this is 4, 3, 3, 3, and 3, something like this. So 3 square plus 4 square plus 3 square plus 3 square plus 3 square. The square of the distance is very huge. Since it's very huge, this is not the best line. The best line you can easily figure out will be the one that goes as close as possible to something like this. So that's how you get to figure out this is probably be the best line, and this best line will start at some y value, will have some slope, and whenever added it should add some constant. That's how you get to figure out the slope, whatever you calculate, dy by dx, everything. That's how you figure out you're gonna need an equation like y equals mx plus c if you want to figure out what could be the next year's predicted value. That's it. So this is a simple example I just wanted to give you guys to understand how statistics is very useful. As a machine learning engineer, if I do not know statistics and if I only know programming language, I'm just a programmer. I'm not a machine learning expert. I'm not a machine learning engineer. For us to be machine learning engineers, a lot of statistical concepts are very hugely beneficial. I'm just giving you a couple of simple examples. There are so many other scenarios where you identify error, where you identify accuracy, where you identify how good your model is using some statistical terms like R squared, adjusted R squared, something like p-value, and so on. There's so many important statistical terms that come up, and all these statistical terms are equally important if you want to have good accuracy in your machine learning model. So this is what I wanted to give you guys as a small intro towards statistics and how useful it is. So we have not gone through any complicated big problems. I've just taken a small example. I hope with this you're able to understand how useful statistics is for machine learning and why it is so useful. So with this, before we end this mini series of this session, I just want to point out that if you are interested in learning machine learning, in learning and understanding machine learning and working through it practically, you can go ahead and jump in directly to our internship course that we have, which begins from 2nd of December. And for registrations, you can just check the information available in this video's description. You can also go through our Quant Masters websites to get to know more. If you're interested, make sure you join this up to be eligible for the highest initially paid salary job in computer science professional world right now. So with this, I hope you have a fun time learning all of this. This is our sixth video, if I'm not wrong, on the mini series of machine learning. If this is the first video you're going through, I would highly encourage you to watch the previous videos where we have taken a look at what is machine learning, what is artificial intelligence, what is deep learning, where does the future of machine learning lie, what are the programming languages you need to learn in order to go through this. We have gone through all of these. So do give them a try, do give them a check if you're interested, and we'll catch up in our next video where we're going to learn a little bit more about machine learning followed by this. So thank you all for joining in. Let's catch up in the next video of this mini series. Subscribe to get to know more about machine learning. Look at the lot of videos that we have in our channel. And again, as always, thank you for joining in, and have a good time learning this, because as we all know, it's the most highest paid job in the world of computer science. So thanks a lot. Have a good time.